Welcome back. This is the first time we're going to write code today. So let's get started. The first thing I want to do is actually show you the traditional hello world program. So what we'll get going with is simply picking up a text editor, typing up the code for that little piece of C++, and try it out and comment on what is going on here. So look at this code as I start typing it, and we'll discuss exactly what it does and how it works. So let's get started. The first thing I'm going to do is move to CSE, to my folder with the class, and I'm going to load a new program. I'm going to call it hello1 because it already exists, hello1 CPP. So if you follow what's up there, all I'm going to do is say that I'm including a specific header called IOStream. We'll see what it means in a second. Then I'm defining a function called main and returning an integer. And there are only 2 lines in that function that I'm typing now. And they're not all that complicated. But there are still a few little gems to actually explain. That's it. That's our first program. We have it there. So let's take a look at what's going on. As I mentioned, the first thing is this line here, where I'm actually including a header file that's part of the standard library of C++ function. In particular, this program, as you expect, is going to print on the console, hello world, and I need to actually have the tools to print the console. That's part of the IO library for input-output, and C++ is using a concept known as streams. So the header is IOStream. Its real literal name is iostream.h, but when we include it, we drop the .h. And we're using, as you notice, angle brackets at both ends, and that has a meaning as well, and we'll come back to it in just a few minutes, actually in the next segment. Then we define a function, and this should be reminiscent of C function. It's called main. It has a return type that you provide before, exactly as in C. Then 2 pair of curly braces for specifying the body of the function, and then 2 lines of code. The first one here is doing all the job. The second one is returning a value. Well, indeed, we set the function returns an integer. Now, what are we returning? By convention, on Unix, any program that terminates without error should return a 0 to say, life is beautiful, we're done, this is a good output for this program, everything worked as expected. So we always return 0, it's good practice. Note that the code would work even if you said void main, it's just that the value you're getting back is undefined and you cannot rely on it. So good practice, stylistic, always return a value, and you would typically return a value that's non-zero to report that there was a problem of some form. People often use even negative value to report serious errors and positive values to report unusual termination, but that are not critical. Now, the more interesting line is the one above, right? That's the one that's really doing the job. And it has this funny structure where we see a name, std : cout, so that's a composite name, and we'll revisit exactly what it means. Then there is this double angle bracket that are basically saying take this and send it to that. So the string is sent to this thing. So what is this thing? Well, it's a global object that represents the standard output as a stream, cout. Cout is the standard output, and that's the object that will deal with formatting anything that you want to send to the standard output. Thankfully, this object by default understands what a string is and knows exactly how to print a string. Then you notice that there is a second one down here, which is actually meant to say, oh, after you print this, also send this thing into the standard output. So we're chaining the outputs. We're sending the string into the standard output, and once this is done, what we get back is a standard output, and we can send another object to it, and it allows us to chain these print statements very neatly. Now, something that's kind of interesting, and if you recall Java, you will quickly understand what this is this std bit. It basically means that the object cout, which represents the standard output, is not directly available to you. It's actually in what Java would call a package, and C++ calls, a namespace. So a namespace is a collection of variables, functions, classes that are grouped together because they are forming a cohesive set of entities. For example, all of them allow you to manipulate standard objects, so they would be in a place. All of them are algorithms, they would be in another namespace. So it's a way to structure your code in cohesive unit, exactly like you use packages and sub-packages in Java. So in Java you can nest packages, in C++ you can nest namespace. That's the same principle. The great thing is that in C++ you can always add any class to any namespace. You don't even have to have defined a namespace yourself. It can be a namespace that's pre-existing, like std, and you can decide to add things into that namespace. You can define your own namespace, or you can leave things in the global unnamed namespace, the top-level namespace. This is where things would go. Like this main function, I haven't said anything, so it belongs to a namespace, the global one. So that's all there is in this program, and we can directly try to compile it and see what happens. So let's do that. So it's fairly easy to do, actually. All I'm going to do is, in Emacs, I'm going to run a shell. So this is the command to do that. And in this shell, I'm going to run the compiler. So that C++ is the name of the compiler. I'm going to give the name of the file, which is lo1.cpp. I'm going to say where I want the input to go. I want the input to be inside lo1. That's the name of my file. And the last bit that's very important is to say which version of the standard we're going to use. So it's -std. And here, let's say that I'm going with the most recent C++ 14, which is the most recent version of the standard. I hit return. And of course, he complains because he doesn't find that file. So I'm in the wrong directory. So let's move to where I place these files. Document, courses, 3150, and then ModA. And repeat the command. And it comes back saying nothing, so presumably the compilation has succeeded. So if we list the directories, you see that I have lo1 star, so the little star tells us it's an executable, and I could actually execute it, and the way to do it is to type /lo1. Hit return, and lo and behold, it says hello world. So the program is behaving exactly as we expect it to, and did the correct thing and produces the output we expected. So going back to the source buffer, what have we seen? We can write that code and we can run it perfectly fine after a compilation phase. So the compilation is using one of the compiler at the command line. It could be G++. Or you can always use the standard name C++, which on any Unix machine will often be G++ or Clang, depending on the operating system. I'm running this on a Mac here, so when I type C++, it actually runs Clang. That's all there is to it, and the command comes down to this. You've seen it in a second ago. You're compiling, giving the name of the source file, where you're sending the output, and which version of the standard you wish to adopt for the compilation. Linking is happening automatically, and that's the funny thing. You might easily forget that a specific process is ongoing. So let me refresh your memory. Why do I talk about compilation and linking? That's because the process for compilation starts with a document. Here it is. And that's my lo.cpp. It's a document, and it's being sent to the compiler. So you're wondering, this goes in, and that compiler, and I'm going to change color, hopefully we'll be able to read this, is a relatively big box. That's my compiler. But it's going to actually have multiple parts embedded in this. And what are those? Well, it's not too difficult to see. There is a compiler, and that's really C++. And the file is being sent straight into that. Now, that's not the only thing that goes there. There is also, coming from a collection of libraries, and that's why I'm going to use a little database symbol to represent it. They are the header files. Header, right? So in particular, it's going to pull the IOStream header file. You've seen it because it says right there, pond include IOStream. So this also goes into the compiler. What comes out of that is a document. Now that document is an object file, and its name is based on the source, right? On this source, it's hello.o. On a Unix, that's always the extension. .o means it's an object file. Now that object file by itself just contains the compiled version of the function main. It's not executable. You cannot run this. You cannot actually see the behavior of that. To actually obtain an executable, so I'm going to repeat, it's an object file. To obtain an executable, you have to call upon another tool, which is known as the linker. Now, the object file goes into the linker along with another database, and I'm going to represent that way, and that's the C++ standard library. That goes into the linker, and it contains the implementation of those IOStream. It contains the implementation of stdout. It contains all of these things. And what comes out is a document. It's your executable, hello. So that's an executable, and this you can run at the command line and do whatever you want with it. Okay? So that's the compilation process for you. We start from a source file. It goes into the compiler along with a collection of headers. This produces an object file, at least one, there could be several. Then this object file goes into the linker along with the libraries themselves. That is the implementation of things like stdout. And this yields an executable. Now, when you invoke C++, what you think is that you're doing is that you're invoking this big dashed box, and it automatically invokes for you these two programs in one fell swoop. Now, there are lots of circumstances where you'd rather not do that, and you'd rather invoke the tools separately. You want to have incremental compilation. Imagine that you have 1,000 files like that to produce one executable. If you edit a single file and leave the other ones untouched, you'd like to recompile only the file that has changed. So you want to recompile that and do the relinking. You don't want to recompile all 1,000 files. So you want to separate the compilation and the linking phase. That's critical, and that's what this is all about. So when you want to do that, thankfully it's very easy to do. All you have to add is first an option that's given in yellow over here, -c. So -c asks only compile. That is, rather than spitting out the executable by doing the linking automatically, it's going to spit out that intermediate object file into a file that you can actually use afterwards with the linker, which is, of course, the second command you see here that basically takes the object file hello.o and does the linking. You notice that we never specify the library. The compiler picks it up automatically based on what you want to do. There is nothing really special about this. So it gets done completely automatically. Now, if you want to run, you've seen it, we use dot, which just means pick up the executable from the current working directory. Pick it up from the current path and run that. So we execute by simply saying, and I'm going to put it over here, ./hello, right? So the // is to simply say, pick up the current working directory. That's where you will find the executable we've just produced, and let's run that. So there is nothing really special about it. we've seen that command too. Debugging, again, it's quite straightforward to do. You can actually get to it by adding yet another option, and I'm going to put it over there in that corner, and that's quite straightforward. It's -G. And -G can actually even take, well, it's just -G. It means add debug information. Right? That's a simple flag, and that's what you get illustrated here. Now you have to add it both to the compilation command and the linking command so that this file gets extra debug information and this one gets it too, so that the debugger can refer to that information to show you your source code when something goes wrong, so that you can actually do the right thing and inspect the state of the program, inspect the variable, inspect the stack, all the kind of things you typically would want to do. So that's it. Next up, we are going to be talking about file inclusion. See you next time.